In the profound and silent darkness, a billion kilometers from the warmth of our sun, a world of amber twilight endures. A sphere swathed in perpetual haze, a mystery wrapped in an enigma, suspended in the deep freeze of the outer solar system. This is Titan, the largest moon of Saturn, a place where the familiar and the alien are woven together in a tapestry of bewildering complexity. For centuries, it was but a pinpoint of light, a golden star in the eyepieces of astronomers. Then it became a smudge, a blur of orange against the black. Its secrets were guarded by an impenetrable veil, an atmospheric shroud that teased our curiosity and defied our gaze. What lay beneath those clouds? Was it a barren ball of ice, a static relic of the solar system's birth, or was it something else entirely, a dynamic, shifting, and strangely Earth-like landscape, operating under rules both recognizable and profoundly strange? The journey to uncover Titan's true nature is a story of human ingenuity, of robotic explorers sent across unimaginable distances, and of a relentless pursuit to understand our place in the cosmos. It is a story that begins not with a spacecraft, but with a simple, profound question asked by a stargazer in an age of candlelight and curiosity. That question was first given form in the year 1655. The Dutch astronomer Christian Huygens, using a telescope of his own advanced design, trained his lens upon the ringed planet Saturn. In doing so, he noted a small, steadfast companion keeping its vigil nearby. He called it simply Luna Saturni, Saturn's moon. It was the sixth moon ever discovered in our celestial neighborhood, but it was immediately distinctive. Even in those early observations, it hinted at an unusual nature. Over the centuries, as telescopes grew more powerful, this distant point refused to sharpen into a crisp, cratered disk like Jupiter's Galilean moons. Instead, it remained a fuzzy, diffuse orb, a clear suggestion that it was not merely a bare rock, but a world enveloped in something more, a world with an atmosphere. This realization alone set Titan apart, elevating it from a mere satellite to a world in its own right, a place with its own sky. But what kind of sky? What was the nature of this veil? For the next 3 centuries, these questions lingered in the realm of speculation. The faint reddish-orange hue observed from Earth suggested complex chemistry at play, chemistry that scatters and absorbs sunlight in peculiar ways. Theoreticians pondered, could it be a thick, smoggy atmosphere, perhaps rich in organic compounds, or was it a thinner haze over a frozen, inert surface? Without the ability to visit, to probe, to measure, Titan remained a tantalizing cipher, a painted globe whose landscape was the subject of pure imagination. All that changed when humanity finally developed the means to leave its own planetary cradle and send emissaries of metal and silicon on voyages of epic discovery. The space age turned speculation into data, and mystery into even deeper, more wonderful mystery. Our first messenger to this amber realm was a humble pioneer, aptly named Pioneer 11. Launched in 1973, its primary mission was a reconnaissance of Jupiter, but using that giant planet's immense gravity as a slingshot, it was hurled onward towards Saturn, a pathfinder for more sophisticated vessels to come. In September of 1979, Pioneer 11 made humanity's first close approach to the Saturnian system. It flew through the plane of the rings, braving a torrent of unknown particles, and turned its electronic eyes toward the enigmatic moon that had fascinated astronomers for so long. The images it returned were, in a sense, disappointing. There was no sudden revelation of mountains and valleys. Instead, the camera saw exactly what telescopes on Earth had seen for centuries: an impenetrable, uniform, featureless orange haze. The veil held firm. Titan was not yet ready to reveal its face. But Pioneer was more than a camera. It was a suite of sensors, and these instruments could perceive what human eyes could not. As the spacecraft swept past, it used the radio signals it was constantly broadcasting back to Earth as a diagnostic tool. By carefully measuring how these signals were altered, refracted, and absorbed as they passed through Titan's limb, scientists could perform a sort of remote medical scan of the moon's atmospheric body. And what they found was electrifying. Titan possessed a substantial atmosphere, a real dense enveloping blanket of gas. The data suggested surface pressures perhaps even higher than those on Earth. And the primary constituent of this atmosphere was not carbon dioxide, as on Mars or Venus, but molecular nitrogen, the same gas that makes up 78% of the air we breathe. Here, in the frozen depths of the solar system, a world had somehow managed to capture and retain a vast shroud of the same inert gas that dominates our own skies. This was the first profound echo of Earth, a whisper of familiarity across 1 billion kilometers of void. But Pioneer detected something else, mingled with that nitrogen, a trace component that would set the course of Titan exploration for decades to come: methane. To the casual observer, methane might seem mundane. It is the primary component of the natural gas that heats our homes and fuels our industries. It is a simple molecule, one carbon atom bonded to 4 hydrogen atoms. Yet, in the context of planetary science and the search for life, methane is a molecule of profound significance. It is a hydrocarbon, the most basic member of a vast family of carbon-based compounds. On Earth, the majority of methane in our atmosphere is biological in origin, a waste product of microbes in wetlands, the digestive processes of livestock, the slow decay of organic matter. Its presence is often a signature of life. But methane is also fragile. In an atmosphere with oxygen and under the bombardment of ultraviolet light from the sun, methane is quickly destroyed, oxidized into carbon dioxide and water. For it to persist in an atmosphere, it must be continually replenished. On Titan, there was no evidence of biology, but there was methane, and it was not just a trace. Further analysis suggested it was a key player. Where was it coming from? What was its role? The presence of this simple hydrocarbon, alongside the familiar nitrogen, transformed Titan from a curious oddity into a priority target. It suggested a world not frozen in time, but potentially a world of chemical activity, perhaps even geological process. A world where the raw ingredients for more complex chemistry, the kind of chemistry that on Earth led to the building blocks of life, were present and mixing. This notion was further tantalized by another of Pioneer's measurements, Titan's gravity. By tracking the subtle perturbations in the spacecraft's trajectory as it felt Titan's gravitational pull, scientists could calculate the moon's mass. Combined with its known size, this yielded its density, and the result was puzzling. For such a large moon, larger than the planet Mercury, Titan was surprisingly light. Its density was too low for it to be composed primarily of rock and metal, like Earth or our own moon. Instead, the numbers pointed to a world made of roughly half rock and half ice. Titan, it seemed, was an oceanic world in the most fundamental sense, but with its ocean likely locked away beneath a thick, frozen crust. The surface we could not see might not be a rocky landscape at all, but a water-ice landscape, as hard as granite in the profound cold. This explained the weak surface gravity, only about 14% of Earth's, a gentle tug that, combined with the thick atmosphere, would make for a truly surreal human experience. The air, 4 times denser than Earth's, would feel viscous, like swimming, and with gravity so slight, A person wearing a simple set of wings could, with a running start, launch themselves into the sky and soar for hours, borne aloft by their own muscle power and the buoyant, dense air. It would be a world made for flight. Pioneer 11 was a glimpse, a single data point on a graph of growing intrigue. It confirmed the atmosphere, identified key components, and raised a host of new, more specific questions. But to answer them, humanity needed to do more than fly by. It needed to stare, to map, to linger, and ultimately to touch down. The stage was set for a more ambitious mission, one that would require patience, international collaboration, and the most advanced robotic explorer ever built. The voyage of Pioneer was a note passed across the solar system. The next mission would be an entire conversation. That conversation began with the launch of the Cassini-Huygens mission in 1997, a monumental partnership between NASA, the European Space Agency, and the Italian Space Agency. The spacecraft, a technological leviathan the size of a school bus, was not merely a flyby probe. It was an orbiter designed to spend years weaving through the Saturnian system, studying the planet, its magnificent rings, and its family of moons, with an array of instruments of unprecedented sensitivity. And it carried a precious cargo, the Huygens probe, built by ESA, a saucer-shaped lander named for Titan's discoverer, destined for a one-way journey to the surface hidden beneath the haze. After a 7-year voyage that included gravitational assists from Venus, Earth, and Jupiter, Cassini slipped gracefully into orbit around Saturn on July 1, 2004. Its long-distance relationship with Titan was about to become an intimate and detailed study. Cassini's toolkit was specifically designed to solve the puzzle of the orange haze. Its cameras could peer in wavelengths of light, invisible to the human eye, in the infrared and the radar spectrum. Infrared light can penetrate haze better than visible light, revealing broad patterns of light and dark on the surface. Radar, by actively sending out pulses of radio waves and listening for their echo, can cut through the atmosphere entirely, mapping the topography of the surface in stunning detail, regardless of cloud or darkness. As Cassini began its first close passes of Titan, these instruments began to strip away the veil, layer by digital layer. The fuzzy orb was transforming into a world. The first global maps were revelatory. Titan was not a featureless billiard ball. It possessed a complex, varied, and shockingly familiar geology. The radar images revealed vast, dark, flat plains, unnaturally smooth and confined to specific regions, particularly near the North Pole. They showed brighter, rugged, dendritic terrain networks of channels that looked for all the world like river valleys on Earth, draining from highlands into lowlands. There were also isolated, circular features that could be impact craters, but they were strangely few and far between, suggesting that Titan's surface was geologically young, being actively resurfaced by some process that erased the scars of asteroid bombardment. And then there were the lakes. In the darkest, flattest areas near the poles, the radar signal returned a perfect mirror-like reflection. This is the signature of a liquid surface, smoother than any solid ground could naturally be. Titan did not just have the ingredients for a hydrologic cycle, it had the cycle in full operation, but this was a hydrologic cycle with a chilling twist. On Earth, the cycle is powered by water, liquid, vapor, ice. On Titan, with surface temperatures of minus 179 degrees Celsius, water is frozen into a state as hard as steel. It is the bedrock, the flowing liquid, the rain, the lakes and seas could not be water. The only substance that could exist as a liquid in abundance under those conditions, given the atmospheric composition, was methane and its two-carbon cousin, ethane. Titan's rivers were carved by liquid natural gas, its clouds were made of hydrocarbon vapor, its lakes were reservoirs of liquefied fuel. Cassini's atmospheric sensors painted a detailed picture of this alien meteorology. The thick nitrogen atmosphere, while similar in composition to Earth's in its major component, is a study in exotic extremes. It is 4 times denser at the surface, a palpable soupy medium, and because it is so dense and so hazy with complex organic smog, created when sunlight breaks apart methane molecules, which then recombine into ever more complex hydrocarbons like ethylene and propane, it creates a powerful anti-greenhouse effect. The haze acts as a sunshade, reflecting much of the feeble sunlight back into space before it can warm the surface. It is a world in a deep freeze, but not a static one. Cassini observed clouds forming, drifting, and dissipating, particularly over the polar regions. It detected evidence of vast storm systems capable of dumping immense quantities of methane rain. But this weather operates on a timescale of Titans, slow and monumental. The moon's axial tilt, like Earth's, gives it seasons, but each season on Titan lasts for about 7.5 Earth years, as Saturn makes its leisurely 30-year orbit around the Sun. Cassini arrived during late southern summer and watched as the seasons turned, seeing the southern lakes shrink and the northern lakes become more prominent, a long, slow transfer of hydrocarbons from one hemisphere to the other, a methane monsoon on a multi-decadal cycle. While Cassini was mapping from orbit, its passenger, the Huygens probe, was preparing for its own, far more perilous journey. On December 25, 2004, Huygens separated from the Cassini orbiter and began a silent, 3-week coast toward its destiny. On January 14, 2005, it hit the top of Titan's atmosphere at over 20,000 kilometers per hour. The friction of entry created a blaze of heat, but the probe's heat shield held. As it slowed, a series of parachutes deployed, braking its descent to a gentle drift. For 2.5 hours, Huygens floated down through the orange sky, a robotic snowflake descending into the unknown. Its suite of instruments tasted the atmosphere, measuring its composition, pressure, and wind speed as it fell. And its camera, the descent imager/spectral radiometer, began to take pictures, looking down toward a surface no human eye or instrument had ever seen. The first images showed only an impenetrable, uniform haze, but as the probe descended, details began to emerge. A world materialized from the abstraction of data. The first hints were patterns of light and dark, like a blurred photograph coming into focus. Then, stunningly, the dark areas resolved into river networks, distinct branching channels cutting through brighter highlands. It was a landscape of uncanny familiarity. Huygens was drifting directly toward one of these dark plains. As it dropped below 1 kilometer, the surface detail became exquisite. The dark area was not a smooth liquid sea, but a complex floodplain. The probe's radar altimeter and imaging system worked in concert, revealing a landscape that stole the breath of every scientist watching. It was a river delta, a dry river delta. Huygens touched down at a gentle pace, making a soft, damp impact. It slid slightly, then settled at a tilt. For 72 minutes, a bonus beyond its designed lifespan on the surface, it transmitted data from an alien world. The images from the surface are among the most profound in the history of exploration. They show a plain strewn with rounded cobbles, set in a darker, finer-grained matrix. The cobbles are not stone, they are water ice, worn smooth by the flow of liquid methane, just as stones in an earthly river are rounded by water. The soil is not mineral silt, but likely a complex aggregate of water ice grains and solid hydrocarbons that have settled out of the atmosphere like sticky snow. The color is a washed-out orange-brown under the hazy sky. The panoramic view shows the cobbles stretching to a distant horizon, bounded by what appear to be low ridges or riverbanks. The atmosphere is so thick and hazy that the horizon curves away gently, the sky a dome of muted light. One of the probe's instruments, a penetrometer, measured the consistency of the surface upon impact. It found a thin, fragile crust, like creme brulee, over a softer, wetter-sounding subsurface. Perhaps most hauntingly, the probe's lamp, switched on as it landed, illuminated the ground, and for a brief moment, the heat from the lamp caused a small puff of methane vapor to rise from the damp soil. The very ground was outgassing the stuff of its rivers. Huygens had landed in a place of past cataclysm, a floodplain that had seen torrents of liquid methane, but was now in a period of arid stillness. It was a snapshot of a world between seasons, between downpours. It proved the hydrological cycle was real, but it left the liquid lakes and seas as features seen only from orbit, not yet touched. The lander's data cemented Titan's status as the most Earth-like world in its processes that we have yet found, a mirror held up in a cryogenic funhouse. Here were rains, rivers, lakes, seas, winds, and dunes, but the rock was ice, the liquid was methane, and the sun was a faint, small disk, providing only 1% of the illumination we receive on Earth, casting a perpetual deep twilight. Cassini's orbital mission continued for 13 years, far beyond its planned lifespan, and with each pass it added detail to the portrait. It confirmed that the dark areas at the North Pole were indeed vast seas of liquid methane and ethane. The largest, Kraken Mare, is larger than the Caspian Sea on Earth. Another, Ligeia Mare, showed a mysteriously changing, bright feature that came to be called the Magic Island, perhaps a transient phenomenon of bubbles, waves, or floating solids. It mapped vast fields of linear dunes near the equator, dunes not of sand, but of plastic-like hydrocarbon particles, shaped by winds into patterns mirroring those in the deserts of Namibia or Arabia. It discovered cryovolcanoes, ice volcanoes, where a slushy mixture of water ice and ammonia kept liquid by internal heat and the antifreeze properties of ammonia, oozes onto the surface, a process that could bring materials from a deep, subsurface ocean into contact with the organic-rich surface. This last finding touches on the most profound question Titan poses, the question of life. Titan is rich in the two fundamental requirements for life, as we know it, a liquid medium and complex organic chemistry. On Earth, the liquid is water, and the chemistry is carbon-based. On Titan, the surface liquid is methane, but the chemistry is still carbon-based, and it is prolific. The upper atmosphere is a vast cosmic chemistry set, where solar ultraviolet light and energetic particles from Saturn's magnetosphere zap simple methane and nitrogen molecules, breaking them apart into highly reactive fragments. These fragments, radicals and ions, recombine into an astonishing zoo of more complex organic molecules: ethane, acetylene, hydrogen cyanide, benzene, and even molecules essential for life, like amino acid precursors. These compounds slowly drift down through the thick atmosphere, settling out as a gentle, continuous organic rain, accumulating on the surface and in the lakes over billions of years. The dunes may be made of this organic fallout. The sand is in essence the building blocks of life, lying in vast quantities across an alien world. But can those building blocks assemble into something we would call alive in a sea of liquid methane at minus 180 degrees Celsius? Water is the universal solvent for life on Earth. Its unique properties, its polarity, its hydrogen bonding, its expansion upon freezing are central to biological function. Methane is a nonpolar solvent. It is inert, cold, and sluggish. Chemistry proceeds at a glacial pace in such cold, yet we must not be overly constrained by terrestrial chauvinism. Life is, at its core, a self-sustaining chemical system capable of Darwinian evolution. Could there be a form of life that uses liquid methane the way we use water, that uses the complex hydrocarbons raining from the sky, not just as building blocks, but as an energy source? Theoretical biochemists have proposed possible metabolic pathways. For instance, life could consume acetylene and hydrogen, reacting them to produce methane and energy. Cassini detected a mysterious depletion of acetylene at the surface, a possible, though highly speculative, chemical signature that something might be consuming it. Perhaps a more promising niche lies not on the frigid surface, but beneath it. Cassini's measurements of Titan's gravity and its subtle wobble as it orbits Saturn provided strong evidence for a global subsurface ocean of liquid water, lying perhaps 100 kilometers below the icy crust, kept liquid by a combination of radioactive heat from the rocky core and the tidal flexing induced by Saturn's gravity. This is a hidden dark ocean, utterly cut off from the surface organic world. But it is water, and where there is liquid water, geothermal energy, and the right chemistry, the potential for life as we understand it increases dramatically. Furthermore, the cryovolcanic activity Cassini detected suggests a potential transport mechanism, a way for material from the organic-rich surface to be carried down into the water ocean, or for material from the water ocean to be erupted up to the surface. At the interface between these two realms, the warm, briny subsurface water and the complex organics from above, in a region of dynamic mixing and chemical gradient, who is to say what novel chemistries might arise? It is a place where the two key ingredients, water and organics, could finally meet under conditions of energy and stability. It is this profound, multi-layered mystery that drives the next chapter of Titan exploration. The Cassini mission, in a final act of planetary protection, was deliberately plunged into Saturn's atmosphere in 2017 to ensure it could never accidentally contaminate pristine moons like Enceladus or Titan with Earth microbes. But its legacy is a roadmap for future discovery. That future is named Dragonfly, scheduled for launch in 2028. Dragonfly is a revolutionary concept, a nuclear-powered, car-sized dual quadcopter drone. Titan's low gravity and thick atmosphere make it an ideal world for powered flight. The conditions are more forgiving than on Earth. Dragonfly will be an aerial vehicle and a sophisticated laboratory combined. It will launch from Earth, arrive at Titan in 2034, and parachute through the atmosphere. Once on the surface, it will begin a mission of leaps, flying from one site of interest to another, covering tens of kilometers at a time. It will land in sand dunes to sample the organic sediments, and then fly to the floor of an impact crater, where liquid water may have once mixed with surface organics in a transient warm moment. Its mass spectrometer, gamma-ray spectrometer, and suite of cameras and sensors will analyze the composition of the surface and subsurface in detail, searching for complex organic molecules and potential biosignatures. It will listen for seismic tremors from Titan's interior and monitor the weather on this alien world. Dragonfly is not sent to find little green men. It is sent to understand the chemical progression toward complexity. It will assess how far prebiotic chemistry has advanced on a world with all the ingredients but a different recipe. Is Titan a frozen snapshot of the early Earth, a laboratory preserving the steps that led to life here? Or has it taken those steps down a different, colder pathway, perhaps yielding a form of life fundamentally alien to our own? Or is it, for all its dynamism, a world that never crossed that final mysterious threshold from chemistry to biology? The answers will reshape our understanding of life's universality. To contemplate Titan is to hold a paradox in the mind. It is a world of stunning, haunting beauty and profound loneliness, a place where rivers flow, but they are carved in ice by liquid gas, where the sky is thick, but it is a poisonous brew, where the sun is a faint, wan disk, and the night is lit by the golden glow of Saturn, a vast ringed god hanging in the orange haze. It is a testament to the boundless creativity of planetary evolution, showing that the processes we consider uniquely earthly, erosion, volcanism, weather, seas, are in fact universal, written in different materials under different laws. Titan whispers that the principles of geology and meteorology are cosmic, even if the substances are alien. But more than that, Titan stands as a profound question mark in the cold outer dark. It is a world soaked in the precursors of life, a world with not one, but two potential liquid habitats, the methane seas on the surface and the water ocean in the depths. It challenges our definitions, stretches our imagination, and forces us to consider life, not as a singular earthbound phenomenon, but as a potential universal principle, capable of arising in the most unexpected of cradles. As we look up from our own blue marble, with its abundant, vibrant biosphere, we can now look toward that golden dot near Saturn and wonder, is it merely a complex organic museum? Or is it, in its silent, frozen way, also a living world? The haze still holds its final secret, but we are coming closer with each mission, each experiment, each daring flight of a robotic dragonfly through an alien sky, to parting that veil forever, and perhaps finding in its amber twilight a reflection not of our own world, but of life's stubborn, ingenious potential in this vast and varied cosmos. The journey to understand Titan is more than a catalog of facts about a distant moon. It is a chapter in the story of human curiosity, a reflection of our deep-seated need to explore, to know, and to find our place in the grand narrative of the universe. From the moment Christian Huygens first discerned that faint point of light adjacent to Saturn's rings, a chain of inquiry was set in motion, a chain that links the polished lenses of 17th century telescopes to the sophisticated radar arrays and mass spectrometers of interstellar robotic explorers. Each step in this journey has revealed not only the secrets of Titan, but also the expanding capabilities of the human mind and spirit. We build machines that can survive the radiation belts of Jupiter, the vacuum of space, the searing heat of atmospheric entry, and the bitter cold of a cryogenic world, all to answer questions posed by dreamers and thinkers generations ago. In this endeavor, Titan serves as both a destination and a mirror, showing us the tenacity of natural processes and the boundless potential for worlds to evolve in astonishing diversity. Consider the sheer scale of time and distance involved in this exploration. The light that reaches our eyes from Titan when we gaze at it through a telescope tonight left that moon over an hour ago, traveling at the universe's speed limit. The spacecraft we send take years, often decades, to complete their pilgrimages. Cassini's 13-year orbit around Saturn is but a blink in Titan's geological timescale, where seasons last for years and methane rivers may flow only once in centuries. This disparity in timescales between human ambition and cosmic rhythm is humbling. It teaches us patience and perspective. Our missions are fleeting glimpses, isolated data points in a saga billions of years old. Yet from these glimpses, we piece together epic histories. We infer that Titan formed in the cold outer reaches of the primordial solar nebula, accreting from ices and rocks, and that it was perhaps warm enough in its youth for its water-ice mantle to melt and differentiate, allowing a rocky core to settle and a deep ocean to form. We see in its thick nitrogen atmosphere a puzzle. How did a world so small retain such a massive shroud? The leading theory suggests that ammonia, abundant in its early composition, was broken apart by impacts or photochemistry, releasing nitrogen, which, being heavy and inert, was not easily lost to space. Its methane, constantly being destroyed by sunlight, must be replenished from a vast subsurface reservoir, perhaps through cryovolcanism or slow seepage from a clathrate layer within the ice shell. Titan, then, is not a static portrait, but a dynamic system in a slow-motion equilibrium, a delicate balance between internal sources and atmospheric destruction. The philosophical implications of Titan are as deep as its suspected ocean. It presents a powerful counterpoint to the notion of habitability as a simple checklist of Earth-like conditions. The traditional Goldilocks zone, the region around a star where liquid water can exist on a planet's surface, is a useful but incomplete concept. Titan lies far outside our sun's habitable zone, in a region where water is eternally rock, yet it has found another way to foster complexity and process. It has leveraged a different chemistry, a different liquid, to create a world of startling geological richness. This expands the cosmic real estate for potential life enormously. Around colder stars, or in the outer systems of sun-like stars, Titan-like worlds could be common. They may be the true abodes of life in the galaxy, outnumbering Earth-like planets. This forces a philosophical shift. Life may not need a sun-drenched, water-filled world. It might thrive in the dark, cold, hydrocarbon-scented depths of a moon-like Titan, deriving energy not from photosynthesis, but from chemical reactions between atmospheric deposits and a subsurface water ocean, or even from the minute energy gradients within the methane seas themselves. Titan challenges our anthropocentric biases and asks us to define life not by its container, but by its fundamental properties of metabolism, growth, and evolution. Furthermore, Titan serves as a possible window into our own past. Before life arose on Earth some 4 billion years ago, our planet's atmosphere may have been rich in methane and ammonia, with complex organic molecules forming in the air and seas, a scenario famously demonstrated by the Miller-Urey experiment. The Earth then was a prebiotic laboratory, a cauldron of organic chemistry. That chapter on Earth is lost, erased by the very life it spawned, and by billions of years of geological recycling. Titan, in its deep freeze, may be preserving that chapter. Its atmosphere and surface may be analogs of that early Earth environment, a natural laboratory where we can observe the steps of prebiotic chemistry unfold on a planetary scale without the overprint of biology. Studying Titan is, in a very real sense, a form of paleontology, a way to look back at the chemical conditions that preceded the dawn of biology on our own world. The tholins, the complex reddish organic polymers that give Titan its color, might be similar to the primordial soup ingredients that on a warmer world could have led to self-replicating molecules. Yet, for all its familiarity and process, Titan remains profoundly, unsettlingly alien. Imagine standing on its surface. The ground underfoot is water ice, but it is not slippery. At these temperatures, ice has no lubricating melt layer. It is as dry and hard as granite. The rocks are also ice. The sky overhead is not blue, but a diffuse dull orange-brown, fading to a darker brown at the zenith. The sun is a small, intensely bright point, but it provides no warmth, casting sharp black shadows in the twilight glow. Saturn, nearly fully illuminated, hangs huge in the sky, a softly banded globe encircled by its famous rings, which would be seen nearly edge-on from Titan's equator, a dazzling thin line cutting across the heavens. The silence would be absolute, broken only by the howl of wind, for Titan does have winds, which shape its dunes and clouds. And if you were near the North Pole during the rainy season, you might witness a methane storm, not a torrent of water, but a slow, heavy downpour of liquid natural gas, pooling into streams and rivers that carve channels through the icy landscape. The smell, if a human could experience it without a suit, is unimaginable, a mix of petroleum, asphalt, and perhaps a hint of bitter almonds from hydrogen cyanide. It is a world that engages a sense of wonder, precisely because it is both recognizable and utterly strange. As we look to the future, Titan is not just a target for scientific study. It is a potential foothold for humanity in the outer solar system. Its abundant resources, water ice for life support, and rocket fuel, when broken into hydrogen and oxygen, hydrocarbons for energy and materials, and a thick atmosphere for aerobraking and buoyancy, make it one of the most resource-rich locales we know beyond Earth. Visionaries speak of future robotic outposts, or even human habitats, floating on the methane seas or anchored to the icy shores. These would be bases for further exploration, for drilling into the subsurface ocean, or for studying Saturn and its other moons. While this remains the realm of distant science fiction, it underscores Titan's unique position as a world that is not merely a scientific curiosity, but a potential node in a future interplanetary civilization. The Dragonfly mission represents the next crucial step in this long dialogue, but it will not be the last. Concepts for Titan orbiters, more advanced landers, and even submersible probes to explore the depths of Kraken Mare are already on drawing boards. Each will peel back another layer of the mystery. They will search for definitive evidence of that subsurface water ocean, perhaps by detecting tidally driven flexing of the ice shell with precise seismometers. They will analyze the complex organic molecules in the dunes and lake beds with even greater precision, looking for patterns of molecular handedness, chirality, or isotopic ratios that might hint at biological processing. They may even attempt to directly detect metabolic byproducts in the atmosphere or at the surface. In the grand tapestry of the cosmos, Titan is a single thread, but it is a thread of dazzling complexity and suggestive pattern. Its story intertwines the fundamental laws of physics and chemistry with the contingent, historical paths of planetary evolution. It shows us that the universe is not just a void, dotted with simple balls of rock and gas, but a place where dynamic, intricate worlds can arise under a stunning variety of conditions. It pushes the boundaries of our understanding of what a world can be and what life might require. As we conclude this contemplation of Saturn's shrouded moon, we are left not with final answers, but with a deeper, more resonant set of questions. The awe inspired by Titan is not the awe of a solved puzzle, but the awe of an opening doorway. Behind that door lies not just the truth about a single distant moon, but potentially a new understanding of life's potential in the universe. The orange haze that once hid Titan from view now symbolizes the frontier of our knowledge, a frontier we are steadily, determinedly illuminating. In the silent, cold, and beautifully alien landscape of Titan, we may ultimately find a key to understanding not just other worlds, but our own place in a cosmos that is far more inventive, far more diverse, and perhaps far more alive than we have ever dared to dream. The voyage continues, the dragonfly will take wing, and the ancient hazy world will in time yield its secrets to the patient, curious descendants of those who first wondered at a tiny golden star in the telescope's field of view. And yet, as we prepare to send our next emissary, our latest understanding reveals that Titan is an even deeper enigma than we had imagined. The Cassini mission, in its death, continues to give life to new discoveries as scientists peer into its archived data with ever more refined tools. A recent reanalysis has cast a dramatic new light on Titan's most fundamental secret, the nature of its hidden heart. For years, the prevailing model, supported by tantalizing evidence, was that Titan possessed a global subsurface ocean, a dark, watery abyss sandwiched between a shell of ice and a core of rock. This ocean was the cornerstone of Titan's astrobiological potential, the place where water and organics might meet. But the new data tells a different, though no less fascinating story. By applying novel processing techniques to the faint radio whispers from Cassini, scientists detected a signature in Titan's gravity field that indicates something remarkable. A colossal amount of internal heat is being generated and lost within the moon. The tidal quality factor, a measure of this energy dissipation, is shockingly low, revealing a world whose interior is working hard, flexing and deforming under Saturn's immense pull. This level of dissipation is not consistent with a serene liquid ocean that would efficiently isolate the deeper layers from tidal stress. Instead, it points to a world where the interior is a thick, slushy, high-pressure ice layer, a place not of free-flowing water, but of a warm, plasticized, semi-solid matrix, possibly punctuated by isolated pockets of liquid water, but not a globe-spanning sea. The ocean, it seems, may not be a continuous layer, but rather a diffuse and intricate network of melt within the ice itself. This finding does not diminish Titan's mystery, it deepens it. It suggests a world where the engine of geologic activity is not a placid subsurface sea, but a churning, viscous, and warm interior, a place where chemistry could operate in confined dynamic cells rather than a vast mixing reservoir. This new model of a slushy interior, punctuated by warm pockets of water, fundamentally reshapes the astrobiological equation. It moves the needle from a potentially vast, but perhaps dilute, aquatic habitat to a series of more concentrated, localized, and chemically dynamic environments. These pockets, heated by the intense tidal friction to temperatures that could be as warm as 20 degrees Celsius, would act as natural distillation chambers, circulating nutrients and organics between the rocky core, the icy shell, and the hydrocarbon soup on the surface. Life, if it exists, would not be spread thinly across a global ocean, but could be concentrated in these oases within the ice, thriving in the warmth generated by the moon's own flexing dance with Saturn. A recent study led by Dr. Antonin Affolter of ETX Zurich models just such a scenario, examining whether the meager chemical energy available in Titan's deep environment could sustain life. The conclusion is sobering yet profound. If life exists in Titan's interior, perhaps subsisting on a simple fermentation metabolism, breaking down amino acids like glycine for energy, its total biomass might be vanishingly small, amounting to perhaps just a few kilograms spread throughout the entire moon. Such a biosphere would be sparse, a ghost in the machine, operating on a knife's edge of energy availability. It would not be a lush global ecosystem, but a tenacious microscopic whisper of metabolism in the deep dark. Yet, over billions of years, even a whisper can leave an indelible signature. The metabolic byproducts of such a sparse population, slowly venting and altering the chemistry of the ice, and ultimately perhaps the atmosphere, could be detectable. The search therefore shifts from seeking teeming oceans to finding the subtle chemical fingerprints of a minimalist but persistent existence. This evolving understanding makes the impending Dragonfly mission not just timely, but critical. While Dragonfly is a surface explorer, its instruments are designed to probe the connections between the surface and the interior. Its seismometer, part of the Dragonfly geophysics and meteorology package, may listen for the groans and shifts of the icy shell above the slushy layer, providing the first direct seismic profile of an alien world's internal structure. The data it collects could confirm or refute the new slush layer model, telling us whether Titan's heart is a placid ocean or a churning, semi-solid mantle. Furthermore, by sampling the complex organics at the Selk impact crater, a site where a meteor strike likely created a transient pool of liquid water that mixed with surface hydrocarbons, Dragonfly will be analyzing a location that mimics on a small scale the kind of warm water organics interface that may exist deep within the moon. Then it will be studying a fossilized example of the very chemistry that might be ongoing in those warm interior pockets today. Dragonfly's role is thus expanded. It is not merely a geologist and chemist for the surface, but a diagnostician for the body of Titan, listening to its pulse and analyzing its skin for symptoms of its inner state. Simultaneously, our understanding of the surface we already thought we knew continues to grow more intricate. Take, for instance, the great sand seas of Titan. Cassini's radar revealed them to be planet-encircling belts of linear dunes, dominating the equatorial regions, covering an estimated 15% of the moon's surface, a far greater fraction than the dune coverage on Earth, Mars, or Venus. These are not mere hills of sand, they are monuments to time and wind, some over 100 miles long, dozens of yards high, and more than a mile wide. For years, a perplexing contradiction clouded their origin. The dunes' streamlined shapes, sculpted around mountains and craters, clearly indicated they were formed by winds blowing from the west. Yet all atmospheric models and measurements suggested Titan's predominant surface winds were gentle breezes blowing from east to west, too weak to move the sand-sized particles that make up the dunes. It was a paradox written across millions of square kilometers. The dunes pointed one way, the winds whispered another. The solution required not just observation, but recreation. Scientists dedicated 6 years to refurbishing a high-pressure wind tunnel, painstakingly simulating Titan's dense atmosphere and low gravity to test how its unique sand, likely aggregates of complex organic tholins, would behave. The experiments revealed a startling truth. The sand on Titan requires winds about 50% faster than previously thought to begin moving. The gentle prevailing easterlies are indeed too weak. The dunes, it seems, are shaped not by the constant whisper, but by the rare shout. During brief, intense seasonal events, perhaps when the sun crosses Titan's equator and triggers atmospheric upheaval, the wind direction reverses and strengthens dramatically, generating powerful westerly gusts that sculpt the landscape. These dune-forming winds are so infrequent that Cassini likely never witnessed them, a reminder that our snapshot of an alien world is just that, a snapshot. The dunes themselves are thus records of rare violence in an otherwise calm environment, archives of Titan's most dramatic weather written in ridges of hydrocarbon grains. Their very presence speaks to the incredible patience of geological processes where a world can wait decades for a storm that will reshape its face for millennia. This interplay between the surface and the atmosphere, between the interior and the exterior, paints Titan as a system of exquisite, slow-motion feedback loops. The dunes are made from the soot of atmospheric chemistry, which rains down and is gathered by rare winds. That atmospheric chemistry is driven by the destruction of methane, which must be replenished from the interior, perhaps through cracks opened by the tidal flexing of the slushy layer. The tidal flexing generates heat that warms the ice pockets, which may occasionally erupt as cryovolcanoes, delivering new material to the surface. It is a closed, self-regulating machine of astonishing complexity, all operating at a tempo set by Saturn's gravitational metronome and the distant ticking of the sun's nuclear clock. Titan is not a collection of isolated features, lakes here, dunes there, a possible ocean below. It is a single integrated planetary-scale entity where the atmosphere, the surface, and the deep interior are in constant, if glacially slow, conversation. And so, we return to the question of life, armed with this newer, more nuanced vision. The possibility does not vanish with the model of a global ocean, it transforms. Life, if it exists, would face a different set of challenges and opportunities within a slushy, pocketed interior. Instead of a vast, dark, and potentially nutrient-poor sea, organisms would inhabit confined, warm, chemically rich microenvironments, possibly connected by slow convective currents within the ice. They would be cut off not only from the sun, but from the vast majority of their own world's volume, living in isolated archipelagos of liquid within a continent of ice. Their energy would come not from sunlight or from hydrothermal vents fueled by mantle convection, as on Earth, but from the sheer mechanical grinding of ice grains against each other, from the tidal heat generated by a relentless gravitational embrace. It would be a life of profound isolation, yet also of profound intimacy with the fundamental forces of orbital mechanics. The biochemistry would be water-based, familiar in that sense, but would have to be adapted to temperatures and pressures, and to a chemical soup enriched by millions of years of organic fallout from above that are utterly alien to our experience. The very solvents of life might be mixed, water with ammonia perhaps, or other cryogenic mixtures that remain liquid at sub-zero temperatures. It is a frontier of biochemistry we have only begun to imagine. This expanded vision of Titan also reframes its role as a cosmic time capsule. If it lacks a global ocean, its value as a direct analog for subsurface oceans on Europa or Enceladus may shift, but its value as a museum of solar system history and prebiotic chemistry only increases. Its surface, untouched by plate tectonics and protected from ultraviolet radiation by its thick haze, is a layered archive. The dunes are piles of atmospheric history. The lake beds are sedimentary records of climate change across millennia. The impact craters are frozen moments where water and organics briefly met. Titan becomes less a candidate for a second genesis of life and more the solar system's premier natural laboratory for studying the chemical pathways that lead toward life. It shows us the steps, the myriad ways carbon, hydrogen, nitrogen, and oxygen can assemble under cosmic conditions. It shows us what a complex organic world looks like when the spark of biology has not yet caught fire, or when it has caught fire in a form so subtle and minimal we have yet to learn how to see its flame. This brings us to the precipice of the Dragonfly era, a moment of anticipation unparalleled since the descent of Huygens. The mission, now confirmed with a launch readiness date of July 2028, represents a staggering leap in capability. It is an exercise in informed daring, built upon 13 years of Cassini reconnaissance. Its planned 2.5-year baseline science mission will see it fly more than 175 kilometers across Titan's surface, nearly double the total distance traversed by all Mars rovers combined. It will do this not on wheels, but on 8 rotors, leveraging Titan's dense atmosphere and low gravity to become the first vehicle to fly its entire science payload between targeted sites on another world. Its itinerary is a carefully chosen geological and chemical tour. It will first alight in the Shangri-La dune fields, a vast equatorial sand sea of organic particles, to directly sample the end product of Titan's atmospheric chemistry. From there, it will make a series of daring leapfrog flights, each up to 8 kilometers long, eventually reaching the Selk impact crater. This crater is the mission's prime target because it holds evidence of a past where the 3 key ingredients for life as we know it, liquid water, complex organics, and a source of energy, came together. The impact that created Selk would have generated enough heat to melt Titan's water ice crust, creating a temporary lake of liquid water that could have persisted for thousands of years, stewing with the organic molecules on the surface. It is a fossilized, natural version of the Miller-Urey experiment, a place where prebiotic chemistry may have been pushed to its very limits. Dragonfly's dragonfly mass spectrometer and dragonfly gamma ray and neutron spectrometer will dissect the chemistry of this site with precision, looking for the molecular building blocks of life, amino acids, nucleotide bases, and assessing how far along the path to complexity this alien experiment progressed. But Dragonfly's ambitions reach beyond mere chemistry. It is a holistic observer of a world. The Dragonfly Geophysics and Meteorology package will measure seismic activity, potentially feeling the tremors of the icy shell adjusting to the slushy layer beneath, or even the distant rumble of a methane rainstorm. It will record wind patterns, atmospheric pressure, and temperature, giving us the first long-term weather station on an alien moon. Its cameras will provide a fly's eye view of Titan's topography, showing us the texture of the dunes, the layering in crater walls, and the intricate patterns of dried riverbeds in a resolution Huygens could only hint at. Every flight will be a revelation, every landing a first contact with a new patch of an ancient, complex world. The technical challenges are monumental. Dragonfly must survive a 6-year interplanetary cruise, a harrowing entry into Titan's atmosphere, and then operate autonomously in an environment where sunlight is 1% of Earth's. Power is provided by a radioisotope thermoelectric generator, and communication with Earth takes over an hour each way. Its rotor systems, while benefiting from the thick air, must operate in an atmosphere where the fluid dynamics are different, and where the air itself is a mix of nitrogen and methane. Its computers must be robust enough to handle the radiation environment of space, yet intelligent enough to navigate to safe landing zones it identifies on the fly. It is in every sense a first, a new paradigm for planetary exploration that bridges the gap between rovers and orbiters, offering the mobility of the sky with the intimate contact of the ground. The implications of what Dragonfly might find stretch to the horizon of our imagination. Should it discover a rich and diverse suite of complex prebiotic molecules, the kinds that on Earth are exclusively associated with biology, it would powerfully suggest that the path from simple chemistry to complex organics is a common, perhaps inevitable feature of planetary evolution given the right ingredients. If it were to find evidence of molecular handedness or chirality, a preference for left or right-handed versions of molecules, a hallmark of life on Earth, it would send a shockwave through the scientific community, a potential signature of a biological process, or at the very least, a profound bias in prebiotic chemistry. Even the absence of such complexity would be a profound result, telling us that the leap from atmosphere-borne tholins to self-organizing systems is not trivial, that Titan represents a fascinating pause in a process that on Earth continued onward. Dragonfly is a mission of context. It will not find life, but it will tell us if Titan is a place where life could have started, or where it did start, in a form we have not yet conceived. It will tell us if the moon is a chemical masterpiece, a biological sketch, or something in between. Looking beyond Dragonfly, To a future still taking shape in the minds of engineers and scientists, we can envision the next steps in this grand inquiry. A Titan orbiter armed with next-generation radar and spectrometers could map the moon's subsurface to unprecedented depths, directly imaging the structure of the ice shell and hunting for the telltale signs of the slushy layer or liquid pockets. A follow-up lander, perhaps stationed at the edge of Kraken Mare, could deploy a floating or submersible probe to directly sample the methane-ethane seas, analyzing their dissolved organics and searching for any potential surface-dwelling or floating organisms that might use liquid hydrocarbons as a solvent. A network of seismometers deployed across the surface could listen in stereo to Titan's interior, creating a detailed tomographic map of its heart, distinguishing definitively between a global ocean and a slushy mantle. And one day, perhaps a deep drill, powered by nuclear heat, could penetrate the icy shell to directly sample the warm, organic-laden environments suspected to lie below, bringing up material from a realm that has been isolated for billions of years. In the very longest view, Titan's destiny is intertwined with that of our Sun. 5 or 6 billion years from now, as our star exhausts its hydrogen fuel and swells into a red giant, its bloated sphere will fill the inner solar system. The habitable zone will sweep outward. Titan, along with the other icy moons of the outer planets, will find itself bathed in a warmth it has never known. Its surface temperature could rise to a balmy -70 degrees Celsius. The perpetual orange haze, sustained by ultraviolet light, will dissipate as the sun's output changes, shutting down the anti-greenhouse effect. The thick atmosphere of nitrogen and methane will then act as a potent greenhouse, trapping the new warmth. The frozen water ice bedrock will soften. The subsurface slush layer may melt entirely, creating for the first time in Titan's history a true global surface ocean of water, topped by an atmosphere rich in organic molecules. For a window of several 100 million years, a period longer than the time it took for life to arise on Earth, Titan will be a warm, wet, organic-rich world, a second Earth in the making at the twilight of our solar system. It is a poignant, almost poetic future, a world that spent its youth in deep freeze, preserving the ingredients of life, may get its chance to cook them only at the very end of the sun's life. Whether any spark of life, dormant in its deep warm pockets, could awaken to inherit this transient paradise is a question for a universe far older than our own. So we return to the present, to the amber twilight and the silent dunes, to the hidden warmth and the chemical rain. Titan is a lesson in cosmic humility and cosmic ambition. It humbles us by showing that our Earth-centric definitions are provincial, that a world can be vibrant and dynamic in ways we never anticipated, using materials we consider inert, under conditions we consider hostile. It ambitious us by revealing a universe of possibility where the principles of geology, meteorology, and perhaps biology are universal scripts that can be performed with an endless variety of stage settings and casts of molecular characters. The voyage to understand Titan is, ultimately, a voyage to understand the conditions for complexity in the universe. It asks, given simple laws of physics and chemistry, given the common materials forged in stars, what are the pathways that lead to intricate, layered, and persistent systems? Does that pathway always, or even occasionally, lead to the self-aware complexity that gazes back and asks the question? Titan does not answer this. It embodies the question. It is a world that has taken the same elementary ingredients that made Earth and woven them into a tapestry of startlingly familiar form from utterly alien thread. In its rivers of methane and its dunes of plastic, in its possible pockets of warm water, and its continuous organic snow, we see not a copy of our world, but a parallel invention, a independent exploration of what a planet can be. As the Dragonfly mission prepares for its journey, we stand at a threshold. We are no longer merely peering at a fuzzy orange dot. We have mapped its seas, measured its winds, and touched its soil. We have theories about its heart. We are now ready to go and read its chemical diary, page by page, site by site. We are ready to listen to its interior tremble and watch its weather change. We are ready to engage with it not as a distant mystery, but as a world to be known. In the profound and silent darkness, a billion kilometers from the warmth of our sun, a world of amber twilight endures. And soon a machine born of human curiosity will spread its 8 rotors against that thick orange sky. It will rise on a breeze that once shaped dunes the size of countries. It will fly over landscapes carved by rivers of natural gas. It will land in places where the building blocks of worlds have gathered, waiting for a reader. The hum of its motors will be a new sound in that ancient silence, the sound of a question asked across the centuries, finally arriving at its destination. The journey continues. The Dragonfly will take wing, and the story of Titan, and perhaps the story of life itself, will enter a new chapter, written not in hypotheses, but in data, transmitted one precious bit at a time across the vast and patient dark.